Hi everyone. Thanks for being here today for the SOFLUX webinar. I'm very excited to have Katherine Turner, who's a postdoc at University of Arizona and NOAA GFDL. Katherine did her PhD at University of Liverpool with Rick Williams, and then moved to the US, back to the US to work with Joellen Russell and John Christine as part of the SOCOM project. And she's been doing some really cool work looking at the role of storms in regulating heat and carbon fluxes in the Southern Ocean. I'm very excited to hear her presentation today, and I will turn it over to you.
Right. Thank you, Channing. Thanks for having me. I am very excited to share with you all some of the work that I've been doing for the past few years. And so yeah, like Channing said, I'm a postdoc at the University of Arizona. I've been working with GFDL quite a bit, and so I have my co-authors here, John, Joellen, and Ron. But this work really wouldn't be possible without a whole host of people, fantastic modelers and ocean and atmospheric scientists over at GFDL. So I do want to give a shout out to them, as well as the rest of the SOCOM community, without whom this work really wouldn't be possible. Um, so my ultimate interest is trying to understand how ocean heat and carbon uptake impact the Earth system response to emissions. So we have this really famous plot here that shows cumulative carbon dioxide emissions over on the x-axis and average surface warming. And we see nearly one-to-one relationship, which means that independent of the pathway of emissions that you've got, the total amount of carbon that you're emitting into the atmosphere can give you a pretty good sense of, on average, what sort of surface warming you're going to get. And the ocean plays a massive role in determining how this works. Because as we translate from CO2 emissions into CO2 concentrations, which then translates to radiative forcing and then surface temperatures, we've got the ocean playing a role in both taking up carbon, taking up heat, and then setting up climate feedbacks so that these signals can all be translated to each other. And so when I think about fluxes, I like to think about heat and carbon together because it's going to be the combination of the two that are really going to determine what our climate system is going to look like in on multi-decadal to centennial timescales. And as I don't think I need to convince anybody of this in this seminar, but the Southern Ocean is incredibly important for setting the ocean's role in both heat and carbon uptake. So the Southern Ocean is relatively small, has about 30% of the ocean area, but takes up 40% of anthropogenic carbon and 75% of anthropogenic heat. And how the Southern Ocean takes up, redistributes, and then stores heat and carbon determines this Earth system response to emissions. And when we're talking about the Southern Oceans, the wind-driven circulation plays a really important role. So on average, we've got these westerly winds going over the Southern Ocean, which drives upwelling of old, cold, and carbon-rich waters. So what that means is that on anthropogenic timescales, the cold waters are able to take up anthropogenic heat, but then these carbon-rich waters have um, a lot of biologically like remineralized carbon. And so then you have a very delicate balance between the ocean being able to take up anthropogenic carbon and then releasing that regenerated carbon back into the atmosphere. But if you're going to look at the Southern Ocean on any given day, I think you'd be quite hard pressed to see the mean westerlies. So the Southern Ocean actually is one of the stormiest regions in the world. So if we're looking at this little animation here, which is from I think August of last year, we've got the vectors that are moving are the winds, and you can see a lot of cyclonic circulation and a lot of storms that are moving around the Southern Ocean. And these storms in the mid latitudes, and especially in the Southern Ocean, where you don't have as much land prohibiting the progression of these storms, you end up getting very strong winds, very large waves. So the colors below are the significant wave height. And when you can see that you've got some significant wave heights of over 10 meters down here. And then as a result of all of that mixing and wind forcing, you can get anomalous air sea buoyancy fluxes. And so, what I'm really interested in right now is trying to understand how the synoptic scale can feed back into longer time scales and really set the climate of the Southern Ocean that we see. And just I love this video, but I just want to share this. This is actually a video of I think it's a military ship going through one of these storms. And this is not a place where you want to be on a boat taking observations. It's incredibly unsafe. And so we I'm a modeler, so I will never have to go out in these conditions. And I have a lot of respect for anybody who does, because it's not an easy, these storms are going to be really important for the climate system, but in terms of getting out there and taking real-time measurements, there's obviously a lot that's hindering us. So as a result, we have to rely on, if we're going to get observations, we really need to rely on autonomous observation platforms. And there's been some great work that's been done by people on using different sorts of observations to try to understand the impacts of storms. So Magdalena Carranza had published this paper last year, which was actually looking at BGC Argo floats to explore the structure of storm-driven carbon outgassing on larger spatial scales. And what she and the team found was that, on the order of hundreds of kilometers away from a storm center, you get this broad pattern of carbon outgassing. And we also have wave glider studies, which are really interesting because they're able to take transects and look at a relatively small area, but over time, as multiple storms can go past, and they've also seen pretty really strong storm CO2 outgassing underneath these events. But of course, because storms are sporadic, continually happening, and also uh, everywhere, but then at the same time very localized, there's still very sparse spatial coverage when it comes to trying to understand what these storms are doing over the ocean. And we're used to there being sparse observations in the ocean, but when it comes to high latitude storm systems, we actually also have observational difficulties in the atmosphere. So underestimating extreme winds for CO2 fluxes can actually be can lead to quite substantial impacts on how you estimate those fluxes. So Sarah Nickford had this really lovely paper where in the Northwest Atlantic, they found a mismatch of about 8% due to not having the exact same wind speeds associated with the CO2 fluxes. And when it comes to the Southern Ocean, oftentimes we rely on reanalyses that have data from satellite observations. But when we're thinking about the observations that we have over on the right panel here, you can see that most of the Southern Ocean gets at most 3 observations of from satellites a day. And so when you're thinking about a fast-moving storm that has really intricate dynamics with it, if you're only capturing something once every 12 hours or 8 hours, you're very likely going to miss the period of extreme winds, which can be the most impactful in setting up your heat or carbon fluxes. Oh, excuse me. Sorry, let me go back. Okay. Yeah. So then the question I want to approach today and discuss with you all is what the role of storms and extreme wind events is in setting heat and carbon uptake in the Southern Ocean. So I will discuss some work that we've recently published in Journal of Climate, looking at how we track storms and the statistics of storms in some of the global climate models that we were using at GFDL, um, looking at storm-centered composites of heat and carbon fluxes in those models, and then exploring a little bit about what the upper ocean seems to be doing in accordance with those fluxes. So um, I in this work that I've done, I've focused on using the pre-industrial runs. So even though I'm interested in anthropogenic heat and carbon uptake, it's really difficult to know what the changes to the system when when the diversity of storms and the diversity of the ocean state can theoretically play quite a large role. So what I've been able to do is use century-long integrations of two of our climate models. At GFDL, we have CM 4.0, which is our standard climate model, and then we have the Earth system model, ESM 4.1. And so with a 100-year long run, we can ensure that we've got statistically robust results across our seasons. And what's also nice is that you can rerun these as many times as possible and they'll bitwise reproduce. So you always get the same storm in the same place, which is really nice. Because I have personally gone through the experience where I've forgotten to save out a variable, had to rerun the entire century. And it's just good that you haven't lost all the storms that you've already been studying. Um, for people who want to know about more about the models, CM4 and ESM 4.1 are very similar. They have very similar dynamics in both the atmosphere and the ocean, but they differ in two substantial ways that can be important for what we're thinking about. ESM 4.1 has a lower resolution ocean. It's got about half a degree with parameterized mesoscale eddies, but it has a more complex ocean biogeochemical model in it, which is called cobalt. CM 4.0 has chosen to simplify the ocean biogeochemistry in favor of getting a higher resolution ocean. And it's a fourth of a degree nominally, so it's still not going to be resolving a lot of small scale processes in the Southern Ocean, but it seemed like the diagnostics of these two models actually show quite strong improvements in CM4 using this setup when it comes to mixed layer depths and things like that. So we've got these two models that are similar in some ways but different. So we can try to understand a little bit about how model diversity might actually impact how we understand what's happening with storms underneath the Southern Ocean. And speaking to a bit of that diversity, if we're just looking at the background climatologies of the Southern Ocean, what we see is pretty shocking. So the heat fluxes and the turbulent heat fluxes between the two models, which are the red and blue lines here, are very similar, which is good, especially since it was uncertain whether the changes in the parameterizations and the horizontal resolution were going to make a big difference. But then the carbon fluxes are incredibly different. So seasonally, ESM4 shows the highest CO2 outgassing in the wintertime. So where positive values for carbon fluxes are carbon going out of the ocean. And this fits quite well with our observations. So with the Landschutzer product, for instance, and BSOSI, with the caveat that we've got to shift because we're looking at pre-industrial conditions rather than current day conditions, whereas CM4 is completely out of phase with that. So CM4 actually shows highest outgassing in the summertime. And while this is very different from our observations, CM4 is actually quite indicative of other CMIP6 models that have biogeochemistry. So we are in they're in the gray lines behind. So we've got a lot. You can choose whatever model you want and get any seasonal cycle you like at this point. And so when we're looking at our storm anomalies, because of this, we decided that we wanted to remove the seasonal climatology. So really thinking about the short term or the short term change that could be induced by synoptic activity. Um, and so then to think about a storm, I do want to go over the classical way of thinking about how a storm develops. And this is the Norwegian model or the Bjerknes mid latitude cyclone model. So um, what ultimately what is theorized to happen is you've got a cool air mass and a warm air mass, and you've got a disturbance that happens along the boundary of those two air masses. Rotation kicks in and starts to move the warm air mass and cold mass cyclonically in a wave stage. And because the cold front moves faster than the warm front, you end up getting a cyclonic circulation where you have a cold front, you're getting a low pressure system, and then fronts following each other. Eventually, that cold front catches up to the warm front and it starts to occlude and becomes an occluded front. And that occluded front leads to the eventual dissolution of the cyclonic system. Um, of course, this is all very highly theoretical, and observable mid-latitude storms rarely ever look like this. And they actually have a wide range of sizes. You can get high levels of asymmetry. You can get multiple sea level pressure minima. The vertical extent or the vertical tilt of these storms can change. So there's actually a really wide diversity of storms that you may want to consider when you're thinking about the impact of a specific event. And so because of this diversity, it's not easy to figure out how exactly you want to find your storms, either in your reanalysis or your climate model. And so you have a lot of options that you can choose. Some of them that have been used before are eddy kinetic energy, sea level pressure variance, geopotential heights, relative vorticity, wind speed by itself, sea level pressure by itself, or a combination of this. And how you choose your variables ends up making quite a big difference in terms of the number and the location of the storms that you are tracking. Um, and so because I'm interested in the air-sea fluxes, I wanted to focus on what's happening at the air-sea interface. And so we decided that we were going to use sea level pressure as our as our detection requirement. So we ended up using Lagrangian storm tracking. So we were able to run the climate model output through this tempest extremes program and track for sea level pressure minima between 30 south and 90 south. We had a few conditions that these minima um, needed to have in order to be considered as a storm, and then the algorithm takes the centers of the storms that it's tracked and then stitches them together so you can create storm tracks. And just to show you kind of how many storms we've got for a 95-year integration or 100-year integration, you have about 1.8 million sea level pressure lows, which are identified. And this translates to about 50,000 storm tracks with 860,000 6-hourly snapshots, which is what we normally have for our atmospheric output, and then close to 250,000 daily snapshots of the ocean variables, which is a lot. So it's a great large data set, and I would encourage if anyone wants to deal with some big data um, with storms that yeah, it would be great to work on this because it is a lot of data. But what do the storms actually like? How do storms actually behave in the Southern Ocean in these models? Um, so the storm statistics that we get actually look quite good. I have over here the storm densities in number of storms within a 5-degree radius per month for the satellite era of Era 5, CM4, and ESM4. I'm looking at both summertime and wintertime densities. And you can see that in Era 5, the storm track surface signals are located mainly between 55 and 65 degrees south, and that during the summer, it is more zonally homogeneous, whereas in the wintertime, the storm track moves a bit further south and starts to have these nodes of activity, especially in the Indian and um, outside the Ross. And so surprisingly, we actually get quite a good fit between the reanalysis data sets and the storm tracks that both the models are able to reproduce. So the GFDO models experience slightly more storms equatorwards, which is not unexpected because we do expect storms to shift polewards under anthropogenic forcing. And we do have some regional biases in terms of where the wintertime storms are located in the models compared to the reanalysis. But ultimately, this is quite good. It gives us a lot. It helps give us a little bit more confidence that mismatches or things that we might be seeing might be due more to the ocean side of things than the atmospheric side of things. And then in terms of what an average storm looks like, we can regrid the atmospheric or the ocean fields into storm-centric coordinates and then create composites of these, 850,000, 215,000 snapshots to see on average what is the storm looking like. So I've got here the sea level pressure, surface winds, sea surface or surface air temperature anomalies, and precipitation anomalies. And ultimately, the modeled composites look good. Our sea level pressure has a local minimum at the storm center, which is fantastic because that's how we've defined it. We get our surface winds that are cyclonic, so going clockwise in the Southern Ocean, and then at their maximum, where the cyclonic circulation lines up with the westerlies, just slightly north of the storm center. We see surface temperature anomalies associated with the equatorward displacement of the cold air mass and the poleward displacement of the warm air mass. And then we get a precipitation anomaly that is consistent with the warm air, which has more water vapor in it, moving forwards. There are some differences between the Era 5 dataset and the modeled composites, but ultimately they do still show the same structures. But then what's really interesting is when you start looking at the ocean flux side of things. So these are the same sorts of storm-centered composites, but now thinking about the anomalous heat fluxes and CO2 fluxes underneath these storms. And so on the right, I have the storm heat fluxes, and we have a really nice picture of this large area of blue, which is heat being released from the ocean into the atmosphere. And then this region of red, so an area where the ocean is actually taking up heat from the atmosphere. And what's really neat about this is that you can see the beginning of, or the cyclonic circulation through this zero sort of contour, and how the cold front, which is here, is starting to occlude with the warm front on average. So you've got a much larger region of heat release because of that occlusion. And then for the CO2 fluxes, what you see is that we've got this large region of purple, which is outgassing, and that is maximum just north of the storm center, and then a very weak area of carbon ingassing. And so on average, the storm, integrated over the entire area, on average, storms release both heat and carbon into the atmosphere, but these structures are very different. So the carbon outgassing occurs at the areas of the strongest total winds that we saw in the atmospheric composites, whereas the heat release follows more of the traditional theory of fronts and air masses that are important in cyclone development. And so what we continued to look at was trying to see, okay, how do these composites change throughout the course of the year? So because we've got so many of these storms, we can separate them by month, by day of year, and then see how these composites evolve. And so what we were thinking was that, the winter is generally stormier than the summer. So if the composites are the same, we should get more release of heat and carbon into the atmosphere in the wintertime than the summertime. But what we saw is that these are just CM4 figures, but that there are changes in the regional structure of these fluxes that actually play an important role, where we can't just scale up by the number of storms on any given day. So these are composites from CM4 centered on February over on the left and September over on the right. So in February, what we see is we've got a larger extent of heat release underneath these storms, but we don't have that local minimum in the northwest quadrant that we had before. Whereas in September, the picture looks a lot more like the average composite that we saw in the previous slide. So then if we were to take our a priori estimate of just scaling our full composite by the number of storms a day, we would get this dark blue line in the back, which shows the maximum heat release in the wintertime. But then when we're looking at changes in the behavior of the heat fluxes underneath these storms, we actually see that in CM4, you get your maximum heat release in the summertime, which is associated with the fact that this area of heat uptake in the February, January composites is actually a lot smaller than it is in the winter months. In February, or sorry, for carbon fluxes, it's less of a shift of the nodes of activity between heat uptake and heat release, and more of just a pattern scaling. And so what we found for CM4 is that in February, your CO2 fluxes are actually much stronger than they are in September. So for CM4, we were actually surprised as well to find that the carbon release is also strongest in the summertime, and then relatively weak in the winter and springtime. And then looking at both of the models to see how this might be sensitive to the choice of model that we're using. For heat fluxes, CM4 and ESM4 have the same climatology, and so unsurprisingly, they have very similar storm heat flux anomalies. And what's interesting is that these anomalies are moderately anti-correlated with the seasonal cycle. So in the summertime, you have more heat available in the ocean. You can then release more heat from your storms. For the CO2 fluxes, the difference between CM4 and ESM4 are actually quite strong. So CM4, as we mentioned before, has its largest CO2 outgassing underneath these storms in the summertime, and it's got a much larger variation throughout the course of the year compared to ESM4. So ESM4 is more stable throughout the year and has its maximum timing of storm-induced outgassing in the autumn and then going into the winter. And then these are positively correlated with the seasonal cycle. So you in periods where you're already outgassing in your background climatology, your storms are able to release more carbon. And so what we've been thinking about now is because these climatologies are not related to the amount of storm activity over the Southern Ocean. then by necessity, they have to be related to what's actually going on in the ocean underneath. So we've been thinking about how we've been thinking a lot about how these seasonal cycles are reemerging in these storm anomalies due to different ocean processes. And kind of what I've been thinking about lately is that these seasonal cycles might be coming through the ability of storms to tap into our seasonally varying reservoir. So we're not just seeing a surface response, we're actually seeing a response where the ability of storm-driven mixing to tap into that seasonally varying thermocline and drive that extra entrainment is actually quite important. So I've just got some schematics here, which are trying to think about this positive correlation between the background signal and the storm driven signal. So for carbon, this could work. Like in the summer, you've got a relatively shallow thermocline, and you can create and so by proxy, you've got a larger vertical gradient of DIC because this stronger and thinner mixed layer is allowing more regenerated carbon to stay below it. And the storms in the summer are slightly weaker, but they're able to more easily tap across this this pycnocline and bring up that carbon below. Whereas in the winter, you've already got your deeper mixed layers, you've already been mixing up a lot of carbon from that thermocline. And so you have younger water with carbon that's been more recently in contact with the atmosphere. And so that may be how, even with stronger storms and more of them, you're seeing weaker signals in the carbon outgassing. This isn't part of the paper, but I just wanted to show this because I think it's really interesting. We can also take composites of the upper ocean, and what we see are consistent dipole patterns. So these are mixed layer depth anomalies where blue is deeper mixed layer depths, surface DIC anomalies, and then sea surface temperature anomalies. And this dipole is interesting because you're able to see that waters north of the storm center are cooler, have more DIC and deeper mixed layers than those to the south. And then directly underneath the center of the storm, you're seeing upwelling signals in your mixed layer depths and DIC, which is kind of neat. And then when we look at the anomalies at depth, you can actually, you can see DIC anomalies and ideal age anomalies that are consistent with Ekman suction. So you're seeing enhanced DIC underneath or very close to the center of these storms, a few hundred meters down. And that's consistent with the age of the water at that depth being older. And you can also see the wake of the storm. So these storms are all kind of coming from different angles. So you see that you kind of get this cone backwards from where the storm was before releasing that or bringing up that additional DIC in old water. Okay, so just to wrap up really quickly, ultimately, I guess this begs the question of like, okay, these synoptic signals can be interesting, but how much of a role might they actually play in setting the climate system and the total exchange of heat and carbon? So it's always a problem of thinking about different scales because we know that the Southern Ocean has very strong seasonal variability. And so relative to the seasonal cycle, the heat fluxes and carbon fluxes are quite small. We're talking about less than 10%. But because the seasonal cycle in the Southern Ocean averages out over the course of a year to something that isn't, close to zero, when we start thinking about the annual pre-industrial uptake and release, we're getting values that are quite a bit larger. So for heat fluxes, the storm-driven heat flux component is about 50%. And then for carbon fluxes, it's very dependent on the model that we're using, but we're talking again an order of magnitude larger than it than it was when we were just thinking about the storm fluxes relative to the seasonal cycle. And so then related to if we want to kind of do a back of the envelope estimate forwards for the impact of storms relative to anthropogenic uptake, we're getting something, around 10 to 20% for both heat and carbon. And I want to emphasize here that for the Southern Ocean's role in setting global climate, it's not just heat and it's not just carbon, but it's going to be the product of both heat and carbon fluxes. So if we are potentially, say, undersampling the role of storms in heat fluxes and carbon fluxes, it's not just that we're missing 80% of heat or that we're only getting 80% of heat and 90% of carbon, but we have to actually take the product of the two. So in this way, not understanding the role of these synoptic scale activities can compound and actually potentially quite like strongly hinder our ability to understand how the Southern Ocean is contributing to the global climate response on lower frequency timescales. So I have take home messages here. I'm at my 40 minutes, so I guess I will wrap up here. But we are ultimately working to understand how mid-latitude storms impact heat and carbon uptake throughout the Southern Ocean through using state-of-the-art global climate models. What we found is that the GFDL coupled climate models can reproduce the broad features of the storm tracks and have average storms that reflect how we understand the theory of mid-latitude storms, and that that heat and carbon fluxes underneath these storms have distinct imprints that can be related to this extratropical storm theory, but also the background seasonal cycles of heat and carbon in the Southern Ocean. And that we also see some interesting upper ocean signals with dipole patterns and interior upwelling, and that while these storms are highly localized, quite small, relatively speaking, area-wise, and sporadic, they can non-trivially contribute to our understanding of longer-term climate. And so the QR code is for our paper. It's open access. If you have any difficulty accessing it, please email me. My email is at the bottom. I won't be able to make ocean sciences, but if you do want to discuss storms, I'm more than happy to talk about it. I'm learning a lot. I'm an ocean scientist, and so learning about meteorology has been a really fun experience, and I'm happy to share that with people. So with that, thank you so much.
Thanks so much, Catherine. That was really, really nice to see. So do we have any questions? Yes, Mathilde, you can unmute yourself if you'd like.
Hi. Oh, hi. Can you hear me?
Yeah.
Okay. Yes, thank you so much. That was really a great talk and very didactic. I thought it was very clear. I guess it's probably a question that you get a lot, and I also get it, and so I'd be interested to hear what you have to say about that. But I was wondering, in terms of the effects of the storms on CO2 fluxes, but more in terms of like carbon sequestration and like long-term trends, do you think that the effects are, for example, compensated after a storm by some inverse fluxes, or do you think that the effect is maybe only in the surface, and does it reflect to carbon sequestration on longer time scales? Or if we don't know that yet, how would we have to, would we have to do to answer this question?
Yeah, so I think that's a really important question because it's very easy to understand like storms versus non-storms is kind of like a sinusoidal pattern, and you would think that they would just integrate to be net zero. Um, as part of the paper, we were able to keep the masks of the storms static. And so we were able to take 10-day imprints of kind of what the ocean was doing out afterwards. And so you do see a partial recovery in the heat and carbon fluxes, but it's not complete. And so I want to better understand kind of how that's working in like water mass space. Because if it was all driven by the heat fluxes at the surface, I would expect it to totally recover. But this irreversible mixing that's happening at the base of the thermocline or the pycnocline is not going to be something that's like once you've brought up that carbon, you can reestablish your pycnocline, but that's going to be different from where your carbon-cline is. Um, and so I think those irreversible processes are quite important. And I think uh, the Toolsey paper as well has talked a little bit about the role of entrainment and that being like a bit irreversible. Um, so there's still a lot of work to be done to understand exactly like how the post storm response is happening. But at the same time, it's really hard to figure out because some of these regions are getting storms every 3 days, and the ocean is not a fast actor, right? So 3 days is not really a lot of time to recover in a way before getting slammed by another storm. So it's tough.
Thank you.
Simon, do you want to ask your question?
Yeah, that was a super interesting talk. I really enjoyed it. Um, and that was just looking at your paper now. A question I had about the storm track densities in winter in that early figure. I think it's figure 3 in your paper, but maybe I should know this. But why is the storm density so strong, for example, on the edge of the Ross Sea, but not on the edge of the Weddell Sea? What's the factor stopping storm generation there?
Yeah, so not a meteorologist, but I can take a guess. I think part of that has to do with the fact that you've got the Andes
To the north side.
in South America that are kind of blocking mature systems from crossing over the Drake Passage. And so I know that the Argentine Basin is an area where storms are being generated. So, and that brings up another good point is that because we were checking for sea level pressure local minima, we can't really capture the wave stage in the beginning
Mhm.
developmental stage of the storms because you don't actually have your low pressure system at that point.
Yeah,
So perhaps by looking at a different metric, we would be able to see signals of more developing storms near the Weddell.
because that was the
Um,
second half of my question, and you've just partly answered it. Is I'm extremely interested in what generates the storms in the first place, because I've done work with sea ice
mm.
change and the influence of that potentially on increasing storms. So I wondered if you had done that, um, if you were able to backtrack in some way and identify that location where they started and see what the factors are. But are you saying that's too difficult to do?
You know what? I don't think it's too difficult to do. I think I haven't gotten to it yet. So
Brilliant. That's a
I
good.
think
That's
it's,
that's
I
encouraging.
think we need to figure that out because as well, like if we're only focusing on these storms that are moving relatively long distances, we're thinking about storms that are already quite mature. So that's why we're in that occluded phase when we're seeing those atmospheric composites. But for things like bomb cyclones, which can be really impactful for sea ice, I'm not. I this algorithm's not super great at detecting them, so we need to be a little bit more creative. And yeah, I'm super interested in trying to get a better full picture about like the life cycle of the storm, the life cycle of the ocean underneath it.
Great. Great stuff. Thank you.
Bruno, do you want to ask your question?
Yes, please. Thank you very much for this inspiring talk, Catherine. I was not aware that there can be an underestimation of high wind speed. I think it has multiple consequences in a heat flux and deepening of the mixed layer. Could you a bit elaborate on that?
Um, I so so Sarah Nickford's the lead of that paper for the Northwest Atlantic. So she I mean, Sarah, if you're keen to pipe up and speak on something, because I don't want to speak on your on your area of expertise, but I'm happy to at least give a bit of a. Okay, I think she's gone. Okay.
I'm happy to chime
hi.
in.
Yeah.
Hi, great talk. But yeah, so what I did was I had USV observations in the Gulf Stream region of the North Atlantic, and I interpolated the ERA5 to the location, and then I did an hourly average of the observations to be more fair to ERA5. And that led to this kind of final number of an 8% reduction in CO2 fluxes. So I calculated CO2 fluxes with in situ wind versus ERA5 wind. So just to give a background on how that was done. But I think other papers have also shown that ERA5 is biased low in the mid-latitude storm track. I could find a reference for you and put it in the chat, but I think it's because it underestimates, like, it doesn't get like where the storms are correctly, and it doesn't get the strength properly. I don't fully know if the root cause has been identified, but it's been, you know, it's been documented in several different cases. And there's also kind of this spatiotemporal mismatch between in situ observations and like a product that's like a quarter degree. So that could also influence it. Does that help?
Yes, yes, of course. I mean that I will pay more attention to that. I presume that all these reanalysis are also bringing some kind of average products on
So yeah, I think for ERA5, the 6 hourly winds are actually snapshots, and the 6 hourly sea level pressures are snapshots. But that being said, you're definitely you are most likely not capturing the maximum that's happening over that 6 hours. So it's also a bit more difficult because even if you're looking at wind work, you're not going to be able to get the actual amount of work that's been happening for that time period.
Yeah, I mean that's quite interesting given the quadratic relationship of Earth-sea exchange. Of course, I presume that we have all that in mind. Okay, well, thank you very much. I have another question, Katherine. Can I, Shani, can I ask another question?
Maybe we can have Marin ask her question first
Okay,
and then go
yeah,
back to you.
yeah.
Thanks.
Sure. Thank you, Katherine, for a really interesting talk. I might have missed this right at the beginning, but do your models include sea ice? And if yes, how different is it between the two models, and what would the influence then be on your fluxes?
Yeah, so that's a great question. Both models use the SIS2 sea ice component as part of OM4. Um, so it so through the density plots, in the summertime, most of the storms aren't going to be, or if they're reaching the sea ice, that's usually near the end of their lifespan, and they're not hanging out around the sea ice or the continent all that long. In the wintertime, obviously the expansion of the sea ice combined with the contraction of the storm tracks does mean that you are able to get a lot more storms in contact with the sea ice. So I have something in my so yeah, so I have here plotted for September and March. The storm tracks are in these pink and orange contours, and then the sea ice concentration is in the color below it, so you can see that overlap happening in the winter time. But and so that does change the composites. So for the seasonally icy, let's see, these are carbon fluxes. The seasonally icy in September, you obviously have a dampened signal for because you've got this lid on top. But then the larger difference actually is in the open ocean, and this is more skewed towards the mid latitudes, like 30 to 40, where in the wintertime you're actually seeing the mid latitudes take up an anomalous amount of carbon, whereas they do their outgassing in the in in the summer and autumn. And this difference is actually larger than the ones in the seasonally icy regions, just because you've got more storms that are hanging out in the mid latitudes for longer.
Okay.
Cool. Did that answer your question?
Yes, in as much as that there definitely is an influence on your fluxes from sea ice concentration, and then how accurately that is modeled in the different products that you're using will obviously have a massive influence on the patterns that you show here. But yeah, thank you.
Bruno, did you want to ask your second question?
Yes, please, Shani. I would like to get back to the CO2 fluxes. I hope that I get it right, but you show some plots where there is a not flux in the north and a down flux in the south. So, is it correct?
Yes, for the carbon fluxes, you mean?
Yes.
Yeah.
So that means that in that situation, the storm is reversing the CO2 gradient to shift from a source to a sink. I would like to be sure that it's what you are seeing, and to understand the process behind that.
So are you specifically talking about what's happening at this very southern edge?
Yeah, the fact that we are shifting from a source to a sink. So that means that there's a strong effect on the PCO2 to change the gradient, the CO2 gradient. So
yeah, so I haven't gone into I haven't looked at the diagnostics of what's driving that carbon uptake. One thing that I can think about is that the easterly winds at this point are actually they're counteracting the westerlies, and so you actually have less wind stress, so your gas exchange coefficient is going to be less. I don't know how that compensates with any sort of biological activity. I don't the biology seems I believe that there is probably some biological role as well, but I don't fully understand it. There is another paper out by Kara Neeson looking at phytoplankton, and I think she has some estimates of biological carbon uptake in that, but I do not remember.
okay. And does it happen for both cyclonic and anticyclonic structure?
So I haven't looked at anticyclones over the Southern Ocean.
Okay.
They're not nearly the blocking patterns in the Southern Ocean are not nearly as common as they are in the Northern Hemisphere, just because they're often set up by orography, which we don't have as much. I don't have as much to set up those standing wave numbers.
Okay. Thank you, Katherine.
One other question about the carbon fluxes that I was wondering, Katherine, is that so in the Southern Ocean, the PCO2 seasonal cycle is thermally driven at lower latitudes, and then at high latitudes, it's out of phase and non-thermally driven. And so I guess I'm still not really quite sure how, like, you might expect there to be a very different storm response in those two different seasonal regimes, which are varying by latitude. So is that, because I know you like said you removed the seasonal cycle up for the CO2 because of the models being all different. But so have you thought at all about whether there could be like this meridional dependence in the storm driven?
So I think the figure that I pulled up for Marin's question kind of speaks to that a little bit. So these open ocean composites are mainly focused between like 40 and 30. So exactly where you're talking about, like the mid-latitude gyres where you would expect your thermally driven CO2 fluxes to dominate. I haven't dissected it into the specific areas because I think CM4 and ESM4 are very different in where they shift between this thermally driven to non-thermally driven, like control on the seasonal CO2 cycle. So that's just unpacking like a can of worms.
Yeah, because the other thing related to that is just like at the point where you do transition between those two phasings, like the amplitude of the seasonal cycle is actually very small. And so there might be certain latitude bands where like the total variance in the surface ocean PCO2 at synoptic timescales is actually really high because the seasonal cycle amplitude is low at the point where you have that transition. So it could be a potentially like sort of there are potentially certain latitudes where the storms could be like most of the total variance, not just being important in terms of seasonally varying, but actually like the total variance.
Yeah, that's a really interesting point. Yeah, trying to make that a bit more granular would be really interesting.
Cool. Well, I think we're actually about at the hour, but that was nice to have a discussion. And thanks so much, Katherine, for a really wonderful presentation. And it sounds like you're happy to talk over email offline with anyone who has follow-up questions, because I'm not sure. Sorry, just realized there was one question in the chat, but hopefully Ming Shi can follow up with you because I think he had to go anyway. So great. Thanks so much, Katherine, and thanks everyone for joining.
All right. Thank you, everybody. Yeah, feel free to email me. Here's my email. So hopefully talk soon. And thank you, Channing, and thank you to the SOFLUX committee for having me.
Great. Bye.